Welcome back to the lab. What happens when a circuit designed for 100 watts needs to handle 1,000? Let's talk about that. When a circuit is designed, many limits need to be considered. The limit of every individual component must be analyzed to ensure the larger design will function as intended. Inductors are typically current limited, capacitors typically voltage limited. Resistors are typically power limited, though there is also a voltage limit. Semiconductors vary wildly depending on the type of device. Some devices like op-amps, microcontrollers, and FPGAs have a power limit, a voltage limit, current limits on I/O, etc., etc. As such, these devices require many different levels of analysis, and the analysis between different ICs can vary greatly. A power limit is just that, power. It doesn't really tell us everything that we need to know when making the required design changes. If the voltage is intended to multiply by a factor of 2 or 3 or 10, it may now fall outside of the voltage range considered safe to touch. In that case, extra consideration must be taken to prevent persons from coming into contact with it, something you don't need to consider when you're within the safety extra low voltage range in the US. Besides that, extra voltage rails may be required. For example, in our uninterruptible power supply design or inverter called Project Darwin, our current shunt monitors have a maximum voltage of 40 volts DC. If our voltage were increased above that limit on the DC input, we would require a separate voltage regulator to ensure that those shunt monitors, that their input voltage requirement is not being exceeded. A lot of extra complexity there. I could ramble on like this for hours talking about examples or pitfalls that can occur in different circuits. However, in a half-hearted attempt to keep this conversation focused, I'll start with some general guidelines and then we'll get into some more specifics. First, do not assume that modifying an existing design is the approach that will require the least work. In many cases, the topology for a switch mode power supply, or any design for that matter, depends entirely on the requirements. For a switch mode power supply, the topology that is the cheapest usually depends on how much output power is required. The topology that has the lowest losses usually depends on how much output power is required. When the voltage or current is increased, you must now analyze every single component in that design again to ensure that there is still enough design margin for every component. Sure, it might look like the schematic is mostly finished when they hand you the design, but there are so many required calculations to actually figure out if the design can handle the increased current or power that you may as well have started fresh. Just pick the best components and topologies for your application from the start, and that might have been less work than modifying that reference design. The only downside to this approach is that it requires a designer to have a full and complete understanding of how the circuit works. Duplicating reference designs and stitching them together without understanding is a quick way to end up with a mess of electronics that doesn't really work. Everyone gets lucky every once in a while, but it's much better to actually understand what's going on in the circuit than get lucky. Not to mention, you'll learn a lot more if you really know what's going on. Second, plan ahead. When you design something, document your work. Capture articles or reference designs that you looked at, document assumptions, take snapshots of datasheets that were critical to your work. I like to capture all of my work in MathCAD. A free alternative that I've used is something called SMath, links down below. This allows me to calculate all the limits of a system, peak currents, RMS stresses, design margin and components, etc., just anything critical to my circuit design. And it enables me to calculate them with variables instead of constants. This enables me to change the value of RMS output current required for a converter. And once that's done, if I've captured my calculations in MathCAD appropriately, if I need to change the output power of the converter, or the input, whatever, the calculations will flow down and provide updated peak stress values for every component from input to output. And that's really useful since then I don't need to duplicate the work of actually doing the calculations in order to update the design. In my opinion, we should all do the hard work the right number of times once. Using MathCAD, Maple, or a similar tool will give you this flexibility. It provides the flexibility to update one of your previous designs quickly, more quickly than you could with anyone else's. Just open your MathCAD sheet, change some variables, and make the part selection changes as required from the outputs of those calculations. Third, don't over-constrain yourself. When a designer makes selection choices for a part, it's really easy to add some margin here, sprinkle a little margin there, add some derating at the end, and by the time that's all done, some components may be way more expensive than they need to be. I've seen designs with tons of design margin. We're talking 3 or 4 times more margin than required. This might not be a problem if cost, size, and if there's no concern for cost, but it's just much better to make a plan for when and how much derating you'll add for each component. Then do exactly that. Execute to your plan. I've seen derating done pretty often in a spreadsheet where the applied and rated stresses are tracked and then the total derating percentage is calculated compared to some target derating value. If you're derating too much or too little, it'll highlight it with like red, for example, and it's really easy to see when you have excessive design margin or component overstress. Now, let's dive into some of that more specific advice. When I want to increase the power output of a converter, 9 times out of 10, I'm being asked to increase current and keep voltage constant. This is a pretty tricky ask. When low current supplies are made, they may use diodes for rectification instead of active switching elements. An order of magnitude increase in current, which means multiplying by 10, will cause somewhere on the range of 10 to 25 times more power to be dissipated in those diodes, depending on how much the forward voltage changes. This is probably going to cause some issues and may demand synchronous rectification instead of passive diode rectification. This change may require a different switch mode power supply controller. A new inductor may be required to prevent saturating the core at the higher output current. The increased current requirement may also require different switching FETs to handle that extra current. In order to achieve the same input and output ripple with that additional current, we'll need to add more capacitance on the input and output too. At this point, we have now probably changed the switch mode power supply controller, the inductor, the switching elements. We've added more capacitance on the input and output of the converter as well. In other words, we've changed everything, every component about this switch mode power supply, except for the enable signal and the 2 feedback resistors. It isn't all bad news though. Increases in output power through voltage may be easier. For a step-down converter, as long as the new required voltage is still less than the input voltage, neglecting drops across the regulator itself, you're probably good to go. Naturally, you still need to consider the increased current on the input of the converter and the additional power dissipated in the converter itself due to the increased current. But the changes may be pretty minimal. For a step-up converter, the starting voltage already needed to be above your supply voltage, so you should be in the clear. Same considerations, more input current, more losses within the switch mode power supply circuitry that need to be considered as heat and handled accordingly. Each application is different. Some topologies use a transformer to achieve the correct output voltage. Again, I'm going to use Project Darwin as an example, shameless plug. Our push-pull converter takes notes from the buck topology, so the output voltage must be less than the input voltage. However, we can use a transformer to multiply the output voltage by the turns ratio. Therefore, to achieve our step-up from 11 volts DC to 250 volts DC, a turns ratio of at least 22.2 is required. In order to leave some room for losses across the regulator, the possibility that input voltage may sag below 11 volts under load, etc., it's good to choose a turns ratio a little higher than that value. I believe we chose a turn ratio around 30. For a topology like this, the transformer will limit the range of our output voltage. Since this is a custom component, changing something like this on the final production board can get very expensive really quickly. You should consider what is likely to change and how likely it is to change as a risk when designing something. For example, we could add an auxiliary winding with 10 or 20 more windings, so you can either put that in series or disconnect it if you don't need the additional voltage boost. Considering this allows you to put in hooks in the design like that, and then add flexibility when required down the load without making part changes or spec changes. There's a lot to consider when changing things about the input or output of a switch mode power supply, but it isn't any more difficult than designing one from scratch. Don't assume that reference designs can be copied and modified easily to perform outside of their original specifications. Instead, expect to analyze every component completely or make an entirely new design to meet the new requirements. Expect that these modifications will require you to have a full and complete understanding of how the circuit operates. If you don't know where to start, find somebody who can mentor you by dropping a note in the comments below. or you can reach out to a teacher or professor near you. I'll do my best to answer all of your questions. Document your work as you go, too. Make your life easy so modifications of your circuit down the road doesn't require complete redesign. If you wait long enough between design and redesign, you might forget everything about it if it happens months or years after your original development. It's really frustrating to go back to something that you designed and realize that you need to completely reverse engineer it because you've forgotten about it. I hope that you find these tips and tricks valuable, and I hope that you learn something about modifying switch mode power supply designs. If you feel like I missed something or you need more information, let me know in those comments. Subscribe to be notified of our future videos where we will finish discussing our new UPS architecture and introduce the concept of closed loop control. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching EE for Everyone, and thank you for staying till the end. Bye!